Okay, scientific measurements. When we record scientific measurements, we do so in a very particular way. We write down all the digits that we are certain of and the first digit that we're not sure about. We estimate. There's information in the estimated digit. We want to keep as much information as we can, and so we write down the estimated digit. But all scientists understand that the last digit has uncertainty in it. So as an example, here are two tables listing carbon monoxide concentrations in Los Angeles County. Here are the years. So this one lists, and this is a unit called parts per million. This one shows 6.9, 6.1, 4.1, 2.5, 1.9 parts per million. So in each of these numbers, the first digit is certain. The last digit is uncertain. If it isn't specified otherwise, we're going to assume an uncertainty of plus or minus 1 in that last digit. So what this suggests, 6.9, that's not what I meant to do, plus or minus 1 in the last digit. Well, the last digit is in the 10th place. So what we're saying is this might be too high by 0.1 or it might be too low by 0.1. So that means we're suggesting a range of 6.8 to 7.0 parts per million. Does that make sense? What would the suggested range be for this 2.5? 2.4 to 2.6. Because we're assuming plus or minus 1 in the last digit. That's the uncertain digit. This table, the numbers have been rounded differently. And so now instead of saying 6.9, they're saying the carbon monoxide concentration is 7. Here the last digit is the first digit also. It is still plus or minus 1 in the last digit. So here the uncertainty that's implied by how that is recorded is plus or minus 1, because the last digit is in the ones place. So then this range is from 6 to 9 parts per million. And this range of 3, what would that be? From between 2 and 4. So that's implying between 2 and 4 parts per million. This table doesn't give us nearly as much information as this one does. These numbers are not recorded as precisely. But we record the number to communicate to other people how precisely those measurements were made. You don't just say, well, I want to do it like this. It's like, well, how closely did you measure it? Any questions? Mm-hmm.
6 to 8, right?
Yes. Thank you. 6 to 8. Thank you. See? First mistake of the day? Yeah. It is important. If you see a mistake like that, please tell me, because other people are looking at that and like, how the heck did she get that? So somebody needs to be brave and say, the emperor has no clothes. Scientific measurements. Okay. So how many digits we record depends on the device we're using. And this is a thing that's going to be really important in lab where we're going to be measuring things. And I will take points off if you don't do this correctly. One expression that may help you remember this is that we read between the lines. Some of the instruments we use are digital, like a digital clock. It just gives you the numbers. Those are easy. You just write down whatever it shows you. The balances are digital. You just write down all the digits. But some of our measuring devices are not. They're called analog devices. They actually have lines, and you have to look at them and figure out where the thing is. So here's an example. This is like a kitchen scale. We're going to ignore the ounces because that's English units, and we are in chemistry class, so we're going to look at metric units. And so we look, and here this is the line that's telling us how much this pistachio weighs. So we have to look at these markings and figure out what they mean. So this big line here is marked 0, and this one's marked 10. And then if you count in between, we can figure out that each line represents 1 gram, right? 1 gram. So what we want to do is we're going to read between the lines. The smallest division is 1 gram. We're going to estimate between. Because when we look at this, we see that this line that's telling us the mass, it's definitely more than 1 gram and less than 2 grams. Do you see that? It's 1 point something. We don't want to just write 1 gram. That would imply it's between 0 and 2 grams. We know more than that. We know it's at least 1 and it's less than 2. So we write down, where should I write this? I'll just write here. So 1 point, and then what we're going to do is we're going to estimate. And different people are going to look at that differently. If the lines are really, really close together, you may not feel comfortable measuring to 1/10 of that little tiny space. Well, go to half then. Say it's either between the line or it's on the line. Some things the lines are so close together. This one I think we can kind of estimate. You just imagine 10 divisions in there. I'm looking at that and it's like, well, it's definitely less than 1.5, right? It looks like it might be 1/4 of the way, so you might want to say 1.2, you might say 1.3. I'll just say 1.2 to agree with the caption on the figure. This implies an uncertainty of plus or minus 0.1. So essentially what we're saying is this is be between 1.1 and 1.3 grams. Okay, that's a lot more information than saying it's between 0 and 2. That's more like a guess. Okay, so we always read between the lines. If the lines on the ruler are 0.1 centimeter, 0.1 is where the line is. We're certain about that, just like the lines here. It's obviously more than 1. We estimate between the lines, we estimate the next decimal place, and so we're going to estimate to the nearest 0.01 centimeters. If you have a thermometer that just has 1 degree markings, 1 degree is the smallest marking, we have to read between the lines. So we're going to estimate 0.1 degrees Celsius. We will be practicing this. Any questions? So let's look at a couple of examples. So here we have a thermometer. And the units on this are degrees Celsius. It's zoomed in so you can't see that. So we're supposed to record this temperature. So there's it's not mercury, it's actually red colored alcohol. But you can see it right there. It's almost behind the 100. And we're supposed to record this temperature. Well, you have to look at, kind of orient yourself on this thermometer, and this line must be the 100 degrees, and this would be 110 degrees. So what does each individual line represent? 1 degree. That tells me I need to estimate the 10th place. So I look at this and I say, well, that looks like it's right on. That would be 103. I'm thinking that's exactly on the 103. But I need to write something in the 10th place. If I think it's right on the line, I'm going to write 0.0. And then the unit, degrees Celsius. Because if I write 103, I'm suggesting it's between 102 and 104. We clearly can tell that it's not that big of a range. It is right there on the 103. So by writing 103.0, I'm suggesting that it's between 102.9 and 103.1. Much tighter range. Okay? Here's a graduated cylinder. The units here are milliliters. This is called a meniscus. It almost looks like a contact lens, doesn't it? Just kind of floating in there. That has to do with surface tension and adhesion and cohesion and all kinds of other fun stuff, and refraction of light. But we'll see when we measure things with liquids that they often have this curved surface. We measure the bottom of the meniscus just because everybody decided that's what we're going to do, and the glassware is calibrated for that. So we're looking at the bottom of the meniscus. That's the bottom of this dark shadow right there. So what do we know for sure? It's 4 point what? It's 4.5 something, right? The bottom of that shadow is, this is 0.5, and this is 0.6. It's more than 0.5, it's less than 0.6. So 4.5 milliliters, but then we have to read between the lines. What do you think? Somebody says 0.59, 0.56. I kind of like 0.58. And since I have the pen, I'm going to write that 0.58 milliliters. If everyone is measuring the same thing, and there's small differences in that last digit, that's considered fine. Because it's an estimate, we're not all going to agree. Any questions? Always read between the lines. And that brings us to significant figures, and how do we decide to round stuff? So we just learned how to record the measurement properly. The precision of the measurement depends on the instrument that we use. So we write that down, but then when we do calculations, funny things can happen, and we don't want our calculated result to imply a precision that is greater or less than what is indicated by the instruments we used. So there are different ways of keeping track of this. One way is to use differential calculus. Would you like to learn that method? A couple of wise guys say, yeah. I don't even remember how to do that. I could look it up and figure it out, but I learned it for PChem in college a long, long time ago, and then promptly said, okay, I don't need that. I'll put that in the back file of my brain. That's a more rigorous approach, but most of the time it's not necessary. So significant figures is a vastly simpler and faster way of keeping track of all of this. Now, unfortunately, a lot of students don't like sig figs. Once you understand them, though, I think that you'll realize that they're not that bad. So if you had trouble with them in the past, give them another shot. Ask me questions and ask me questions until that light bulb goes on. I live for that light bulb in students' eyes. Their eyes light up and they finally get this thing, and that'll keep me going for weeks. Okay, so I want to see some light bulbs. So significant figures are significant digits. In a recorded measurement, these are all the certain digits plus the first uncertain digit. So in a properly recorded measurement, all the certain digits, the estimated digit is the last digit. More sig figs, more certainty in the measurement. So the first thing we have to do is learn how to identify what are the significant figures. And really the thing that's confusing here is zeros. All the non-zero digits are significant in a correctly recorded measurement. So those non-zero digits in 13.301 are the 1, the 3, and the 1. That's a zero. We'll talk about those in a minute. 0.00421, the 4, the 2, and the 1. Those are the non-zero digits. Okay. The zeros are what is confusing. There's 3 kinds of zeros. There's trapped zeros, there's leading zeros, and there's trailing zeros. So the interior zeros or the trapped zeros, those are always counted as significant figures. So here, this 0 is trapped between non-zero digits, between a 4 and a 3. That's going to be counted as a significant figure. These zeros, they're trapped. So the ones you have to watch out for are the trailing zeros and the leading zeros. Leading zeros, they come at the beginning of a number. The only reason we ever put zeros at the beginning of a number is to hold the decimal place. They are placeholders. They do not imply measurement. And so here we're talking about these zeros at the beginning of the number. It doesn't matter if they're before or after a decimal point. If they're at the beginning of the number, before the first non-zero digit, they don't count. They're important, but they are not significant figures. Okay? Leading zeros never count. Trailing zeros. Now, the description I'm giving you here is a little bit different than how the book explains it, but it's going to give you the same result. So pick one. If you like the book's method, go for it. This makes more sense to me, and so it's easier for me to explain. It seems to work for students. So those trailing zeros. Sometimes they're significant and sometimes they aren't. And whether they're significant or not has to do with the presence or absence of a decimal point. So trailing zeros are the ones that come at the end of the number. So these are trailing zeros. They're coming at the end of the number. If there's a decimal point actually written in the number, then you count those. If there's no decimal point, like these numbers, then you don't count the zeros at the end. The reason is that these zeros are necessary to hold the implied decimal point. If I didn't write these zeros instead of 100,000, I'd have the number 1. Those are very different. And if you don't agree, I'll buy your house for $1 instead of $100,000. Then you're like, oh, yeah, I guess they are different. The zeros here, if I didn't write those zeros, 1.432000 or 1.432, same magnitude. The amount is the same. What those zeros add to the number is that they show me that that is a very, very precise number. It has uncertainty. I don't even know what that digit is. Tens, hundreds, thousands, 10,000s, 100,000s, millions. To the nearest millionth. If I leave the zeros off, that changes the uncertainty. It doesn't change the value of the number. These zeros without the decimal point, these zeros without the decimal point are there just to hold the decimal place. Any questions? You will have some. Some of this you will get practice on in a worksheet in lab today. So measured quantities have uncertainty. There are some numbers that do not have uncertainty. They are called exact numbers. And if we're looking at how many significant figures does a number have, you could say that they have an infinite or unlimited number of significant figures. 3 kinds. Exact counting of discrete objects. Okay, so here's my keys. Maybe that's not the best example. Let's go with fingers. How many fingers am I holding up? 2. Is there any uncertainty in that? You sure it's not 3? 1, 2. 2 fingers, right? So if I wrote that down, could I write 2.0000000000000 fingers? It's exactly 2 fingers. I could write as many zeros as I want. That would get really tedious, though, wouldn't it? So we don't write the zeros because it would really go on forever, but we have to understand that when we're counting discrete objects, that it's an exact number. Another example is integral numbers, integers, that are part of an equation. Okay, so what's an example of that? The diameter of a circle is twice the radius. It's exactly twice the radius. This is an integer number that's part of an equation. That is an exact number. We're not going to say, oh, it has one significant figure. It has an unlimited number of significant figures. And the other one that we'll run into are defined quantities. 1 dozen is 12 things. It's exactly 12 things. You go to the store and you buy a dozen eggs, it's always exactly 12 eggs. It's not 12 and a half eggs. It's not 11 and a half eggs. That would be messy, wouldn't it? Half of an egg. They're defined. Now, some of the conversion factors are defined quantities and others aren't. And that can get a little confusing. So basically, if you're converting within the same system, then those are exact. And if you're going between systems, they're not exact. So what does that mean? If I'm
Centimeters.
yeah, like inches to well, that's an anomaly. Let's not talk about that one. If I'm going inches to feet, so that is within the English system. A foot is exactly 12 inches because we set up the system that way. If I'm doing meters to kilometers, it's exact. I'm within the metric system. If I'm going between the metric system and the English system, most of the time, it's not exact. The inches to centimeters is an exception. That conversion gets used so often, they actually redefined the size of the inch so that it is exactly 2.54 centimeters. So 1 inch is exactly 2.54 centimeters. Okay? I will not try to trick you with that, but it will come up, and so I do want you to be aware of that. Okay? So let's do some examples. How many significant figures in each of these numbers? So 554 kilometers. How many sig figs? 3. That is a whole number, isn't it? 550 north. 50 north. What? 554. There's no point something, something, something. Sometimes we look at a whole number like that and we say, oh, well, that must be exact. No, it's a measurement. It's not counting. You can't count kilometers any more than you can count inches. It's a length, and there's uncertainty in the measurement. So that one has no zeros. You count the number of digits, 5, a 5, and a 4, 3 digits, 3 significant figures. Letter B, 1.01 times 10 to the 5th meters. 3 sig figs. Okay, so this number is in scientific notation. And this 0 is trapped, so we can count that. This times 10 to the 5th business is holding a decimal place. So this has 3 sig figs. If we wrote that in decimal notation, it would be 1, 0, 1, 1, 2, 3 meters. Okay, and there we have a trapped 0, and then we have these trailing zeros. Technically, the trailing zeros are ambiguous, but we're going to always assume the worst and say that they're not significant. But this number is a bit confusing. We're not sure. Are those significant? Are they not? Is maybe this one significant and the rest aren't? We don't know. And so writing in decimal notation when you've got these trailing zeros is dangerous. It's not necessarily wrong, but it's dangerous. I would avoid it. In this one, it's very clear. When a number is written in scientific notation, we don't have to worry about zeros. There will never be a leading zero, and the trailing zeros will always be significant because there would have to be a decimal place. So you're counting all the digits before the times sign. The 10 and the 5 do not count as significant figures. How about 1.4500 kilometers? 5 sig figs. So we have some zeros there. Those zeros come at the end. There's a decimal point in the number. That means we don't need them for placeholding. They are there because we mean them. Okay, so those count. 7 pennies. How many sig figs? I heard 1 and I heard infinite. There's only 1 digit written. But can you count 7 pennies exactly? Yeah. If you can't, then there's a lower math class you might need to take. So that is an exact number. Exact. If you're pressed to give a number, it says how many, then you could say an infinite number of sig figs. How about 0.00099 seconds? 2. Those zeros come at the beginning of the number. Those don't count. 21,000 meters. 2. Trailing zeros, no decimal point. I'm teaching you to say that those are not significant. So this number, 21,000, where is the uncertain digit then? The uncertain digit is the last significant figure. It's the 1. Sometimes we underline the last significant figure. What we learned was, unless it says otherwise, it implies plus or minus 1 in the last digit, the uncertain digit. So this would be plus or minus 1,000. So this is implying a range of 20,000 meters to 22,000 meters. Does that make sense? It's really more of an estimate. When I say it's 30 miles from my house to Fresno City College, I'm not meaning that it's exactly or that I measured it to the nearest tenth of a mile. I'm saying it's about. It's definitely between 20 and 40 miles. Any questions? So in calculations, your calculator does not understand sig figs. It'd be really awesome if they did make one that did, but they don't. So we have to watch out for the sig figs because we shouldn't gain or lose significant, well, not the significant figures. We shouldn't gain or lose precision just doing a mathematical operation. If I measure something as 1 foot long, and it's between 0 and 2 feet, and then I divide it by 3, and my calculator says 0.33333333333 feet. Did I suddenly gain all this precision just because I divided that estimation by 3? No. It's still just an estimate, a very uncertain number. And so we have to have some rules so that we can keep track of significant figures and we don't gain or lose precision just by doing math. So that's the reason for these rules. So we'll start with the one that's easier for students. Multiplication and division are mathematical functions that are essentially the opposite of each other. And so they share the same rule. When you're multiplying or dividing, the answer you come up with has the same number of sig figs as the factor with the fewest. So the example here, we've got 1.052 times 12.504 times 0.53 equals, this is what your calculator may show you. I would encourage you to write that down. It's a useful number, but then to report the actual answer, we should round it. So what we do is we look at each of the numbers we were multiplying. 1.052, that's a trapped 0. This has 4 significant figures. 12.504, another trapped 0. This one has 5 significant figures. 0.53, leading 0, we don't count him. 2 sig figs. This is the tricky part. What's smaller, 4, 5, or 2? 2. So you look at how many sig figs and you pick the smallest one. Then you take your answer that your calculator gave you and you pick out 2 sig figs, okay, so the 6 and then the 7, that's the second one. That's the one that I'm going to stop at. And then we have to round appropriately. We've got another slide on that, but so I'm going to keep this place, this tenths place, I'm going to get rid of the next digit. And so I ask myself, is that less than 5? Yeah, just cut it off. If it's 5 or greater, we're going to round up. So let's look at division. 2.0035. 5 sig figs here, dividing by 3.20. That's got 3 sig figs because of the trailing 0 with the decimal point. So calculator shows me this. 3 is the fewest number of significant figures. So I want to round this to 3 significant figures. The 0 at the beginning doesn't count. Don't count that one. So we're going the 6, the 2, and the 6. That's the third significant figure. And I want to chop off the number there. I look at the first one that I'm getting rid of, 0. Less than 5, so I just cut it off. And my answer is 0.626. Any questions? Adding and subtracting. So here we have the answer with the same number of decimal places. Not significant figures, but decimal places. same number of decimal places as the quantity with the fewest. So one way to do this is to stack it up like you were going to add without your calculator and draw a line. So we've got these numbers, 2.345, 0.07, 2.9975. So I'm going to stack them up so that the decimal points line up, and then I'm going to sweep across from left to right until I find the one that ends first. So the 0.07, its last digit, its uncertain digit, is in this second decimal place. So I'm going to draw this line to the right of that. This number has 2 decimal places. I want my answer to have 2 decimal places. The top number had 3 decimal places. The bottom number had 4 decimal places. It's the smallest number of decimal places. So you do the math. This is the answer, 4.215. And then where that line is, that's where you're going to cut up the number. The next digit is 2, so I round down to 5.41. We talked about the implied uncertainty. It's always plus or minus 1 in the last digit. So what would the uncertainty in 2.345 be? Plus or minus what? 0.001. Because the last digit, the uncertain digit, is in the 3rd decimal place. So this would be plus or minus 1 in the 3rd decimal place. How about on this one, 0.07? Plus or minus 0.01. And what about the one on the bottom? Yeah, 3 zeros and a 1. You see what I'm doing there? Because this is going to be important in lab. The uncertain digit, we assume that it's plus or minus 1 there. So if we look at these, which of these has the biggest uncertainty? 0.01 is larger than 0.001. 0.01 is larger than 0.0001. This is a bigger uncertainty. And so I don't want to express this answer and say, well, now, just because I added them, that I know that this is to plus or minus 0.0001, because that would be misleading. I need to have the largest uncertainty of any of my numbers. It's just a different way of thinking about this rule. If it's not making sense to you, just plug your ears and go la la la, and I'll wave at you when you should unplug them.
But it's like least precise.
Yeah. The least precise number determines the precision of the final result. So this one, here we're subtracting, same rule. 5.9, this has 1 decimal place. We're subtracting 0.221, and the calculator shows us 5.679. This is the least precise number. It only has 1 decimal place. And so we're going to round the final result to 1 decimal place. The number of significant figures doesn't matter. It can change. It could go up, it might go down, it might be completely different than any of the other numbers. We're looking at decimal places. So here we're keeping the 6 and we're chopping off the 7. The 7 is 5 or greater, and so we need to round up, because 5.679 is closer to 5.7 than it is to 5.6. That's the idea behind rounding. Any questions? So rules for rounding. You round down if that first first digit that you're dropping. I made a new word. A drop digit is a dridget. Okay, we'll see if that takes off. If the first digit is 4 or less than 5, you round down. If it's 5 or more, you round up. There are different classes or different professions where they do an odd-even rule. We're not going to mess with that. Okay, this is really important. Do not take your thinking cap off when you enter the room. Keep it on. Tie it on tight. What happens is that sometimes when students round a number, they change the size of it. That shouldn't happen. Okay, so if you're rounding to the tens or the hundreds or the thousands place, be careful. If you're rounding to the ones or the tenths, you're going to be fine. It's those larger ones. So let me make up an example. I don't know. Well, let's not use miles. Let's say that's meters. So I need to round this to 3 significant figures. Okay, so I'm going to keep the 2, the 1, and the 5. That's my uncertain digit, my last significant figure. I look at the first digit that I'm dropping, the digit, and it's 5 or greater. I need to round up. So this should be 216. Is that my answer, 216? The original one was 215,743. But I see students do this all the time. They'll round it and say, oh, it's 216. Well, again, let's do some real estate transactions. You're asking $215,743 for your house. I'll give you $216. Yeah? That's not good. It's completely different. So when this underlined digit is to the left of the decimal point, when it's above the ones, tens, hundreds, thousands, be careful. So if I'm going to keep this in decimal notation, what I have to do is I have to put in some trailing zeros that are just holding the place. So, because I'm rounding this to the nearest thousand. It's 216,000. I have to indicate that. Okay? So you can do it that way. A safer way is you recognize, ooh, I'm rounding over here. I need to be careful because I've screwed this up before. Put it in scientific notation. So if we put this number in scientific notation, we get 2.15743 times 10 to the, and so the decimal point was right here. So we're moving the decimal point from here to here, 1, 2, 3, 4, 5 places. The decimal point always goes after the first non-zero digit. So that's where I moved it over here. I moved it 5 places. So this exponent is 5. And then sometimes you have a hard time remembering, is that negative or positive? The way I think of this is I look at this number, 215,743. Is that a big number? Yeah, it's a big number. How do I feel about big paychecks? Positive or negative? I feel positive about big paychecks. I have a positive exponent on my big number. I have negative feelings about small paychecks. So now I can take this number in scientific notation. It would still have its unit meter. And I can say, oh, I need to round it at the 5. And the 7 is larger, 5 or larger, so I'm going to round up. And so I'm going to get 2.16. Get rid of the rest of those. And then just write in the times 10 to the 5 meters. And I'm safe. Okay? Well, watch out for that. This is just examples of rounding to 2 sig figs. Let's just look at this one. 5.349. So if we're supposed to round to 2 significant figures, I'm going to keep the 5 and I'm going to keep the 3. I look at the next digit, the digit. I like that, digit. The first drop digit. I do not start at the end and round up and down all the way across. Because if I did that, this 9 would round the 4 up to a 5. That's messing things up. I just look at that first digit, the 4. That's less than 5, I round down. So this rounds to 5.3, not to 5.4. 5.35 rounds to 5.4, but this does not. Any questions? We sometimes have multi-step calculations. We don't want to have rounding errors. If you round at every step, sometimes those rounding things will cause your final answer to be skewed either to the big side or to the small side, and we don't want that to happen. So what we do is we keep extra digits and we round at the very end. My rule of thumb is keep 2 extra digits. You can keep more if you want to, but keep 2 extra digits. And you have to keep track of what you're doing as you're going along, because a problem like this where we have multiplying and subtracting mixed together, you can't just say, oh, well, the smallest number of sig figs is 3, and so my answer is going to have 3. It actually ends up having 2. You also can't say, well, this has 2 decimal places and that the smallest number of decimal places. You can't do that either. You have to look at each operation separately. So in this example, here we have parentheses around the subtraction to emphasize that we have to do the subtraction first. Orders of operation are important. Maybe you've heard of PEMDAS or please excuse my dear Aunt Sally. So P. Why am I blanking on that? Parentheses, thank you. Parentheses, E for exponents, M for multiplication, D for division, A for adding, S for subtracting. We're going to do this subtracting first because it's inside parentheses. So when we subtract those, we're going to write down the number. This result, the calculator shows us 0.479. I underline this 7 because the rule for subtracting tells me this has 2 decimal places. This result has 2 decimal places. So this 7 is the last significant figure. I keep the 9, though, because I don't want to round it and cause an error. And then I've got my other numbers, this times this time. Now I've just got multiplication. I multiply those. I write down what my calculator gives me. And then I look, how many sig figs? Well, this one has 3 sig figs. This one has 4. This one, because I underlined the 7, that only has 2 significant figures. The 0 doesn't count. And I've got 2 sig figs here because of where this number came from. And so this tells me that I have to round this to 2 significant figures. I keep the 1 and the 9. The next digit is 1, so I just chop those off. It's 19. Any questions? Let's do a couple of examples. I know we're running late on time, but we'll be okay. Those ended up looking very squished together. Oh, well. So get your calculator out. Make sure that it understands what you're telling it. So we want to do this. This first one is multiplying and dividing. We don't have to worry about combinations or anything. We can just do the math and write down the final answer first. So 0.10007 is 9.441 times 0.301 equals. Okay. So tell me if I screwed up. I'm getting 0.880959602. Anybody else get that? I did not. I multiplied. Okay. So scratch that. I was testing you. No, I wasn't. I was being stupid. One of the things I like about the TI-36X Pro is that I can see what I actually did. And so instead of just having to do all of that over again, I can go in here and I see that I left off the divide by 2.313 at the end. I can put that in, and now I'm getting something very different. I'm getting 0.3038. Is this looking correct? 73153. Okay. It is so easy to make a mistake punching numbers into your calculator. I like to minimize the number of times I have to punch stuff in, because every time you punch something in or write something down and type it in again, you have an opportunity to make a mistake. I also recommend on a calculation like that, if you don't have a whole crowd of people to check your work, do it twice and see if you get the same result. Because chances are, if you made a mistake, it was just a random one, and the answers will come out different. So if the answers are different, then go for best 2 out of 3. So there's my result. Multiplying and dividing, I'm going to look at number of sig figs. So that first one has how many sig figs? 1, 2, 3, 4, 5, 6. And the second one has how many sig figs? 4. And the third one? 3. And the fourth one? 4. Okay, so you have to be able to count the sig figs. So then I'm going to look and, okay, the smallest is 3. I'm going to round this to 3 sig figs. The leading 0 at the beginning doesn't count. I always write that 0 before the decimal point because sometimes decimal points get so tiny you can't see them. The 0 ahead of it calls attention to say, hey, look, there's a decimal point hiding here somewhere. So I'm going to keep the 3, the 8, and this 0 place. I look at the next digit. It's 5 or greater, so I round up, and I express my answer as 0.381. Any questions? Let's do this next one. 0.881 plus, that was the wrong button, plus, okay, 132.1 minus 12.02 equals. So I've got 120.961. Just yell at me if I do it wrong again. The rule for adding and subtracting is smallest number of decimal places. What's the smallest number of decimal places among these 3? 1. This number in the middle only has 1 decimal place. 0.1. This has 3 places after the decimal point. This has 2. So that means I'm going to round my number, my answer, to 1 decimal place. The next digit is a 6, which means I have to round the 9 up to a 10, which rounds the 0 up to a 1. And so this is going to be 121.0. The 0 there is a significant figure. Don't leave it off. That'll change the precision of the number. Any questions? Okay, let's do this one. Here we've got multiplying, dividing, and adding. We have to do what's in parentheses first. So you can do this without writing any numbers down, but I would recommend writing a number down. So 44.11 plus 1.223 equals. Okay, so when I do what's in the parentheses, I get 45.333. What I want to do is keep track of the sig figs in that result before I finish the calculation. Adding, I'm looking at number of decimal places. Here I've got 2 decimal places, and there I've got 3. This result, if it was our final answer, would only have 2 decimal places, so I'm going to underline the second decimal place. That tells me, when I look at this, this has 1, 2, 3, 4 significant figures. That's important because now I'm going to multiply and divide, and I need number of sig figs. Right? This one has 4 sig figs, and this one has 5. And this one has 4. So my answer is going to end up with 4 significant figures. So 2.5110 times 21.20 divided by that 45.333. The entire result is 1.174270399. And that's a 7. I need to keep 4 significant figures. So I'm going to round right here The next digit is less than 5. So I'm going to get 1.174. I forgot to box this guy. Any questions?
I just wanted to clarify.
Mm-hmm.
So if it was, say we multiplied it by 21.2 without the zero, and it's 3 sigs, is it based on the first calculation we did, or is it based
Okay,
on the
it's a good
least
question.
amount of sigs?
So what if this was just 21.2 and it wasn't 3 significant figures? It is based on the numbers that you're multiplying and dividing. So we had to do this addition first, and based on the addition, we realized that the sum of those has 4 significant figures. So that's 4 significant figures, but then, here, let's actually go in and make it so. Where am I get lost in here? If we make it like that, so now that that has 3 significant figures, then 3 is the smallest number of significant figures. This gets rounded to 3 significant figures, and we'd write the answer as 1.17 instead. That's a good question. Okay? You can apply the rule for multiplying and dividing to a bunch of different multiplying and dividing. You can apply the rule for adding and subtracting when those are mixed up together. But when you have adding mixed with multiplying or dividing, then you have to look at the individual pieces separately. Okay? Oops. Here. Okay, let's look at this one. Here we have multiplying in parentheses. We have to do that one first. 12.01 times 0.3. So that result is 3.603. Multiplying goes by number of sig figs. 12.01 has 4 sig figs. 0.3 has 1 sig fig. So this number has 1 significant figure. And then I'm going to add the 4.811. And so the calculator shows me 8.414 as my answer. I'm taking this number, the result of that calculation, and I'm adding this one. So I look at the number of decimal places in this number, which is no decimal places, the uncertainty in the ones place. And here I have 3 decimal places. So this is uncertainty in the ones place, so my answer is going to have uncertainty in the ones place. Excuse me, and I'm going to round that to 8. Any questions? You're not going to have numbers that round to 0. They might round to really, really small things, but we're not going to end up with things that round off to 0. Any questions? Yes?
When it comes to trailing zeros, I can't really tell whether significant and they're ambiguous.
So trailing zeros, look for a decimal point. If there's a decimal point actually written in the number, you count them. No decimal point, no count. Okay? So if the decimal point is there, you do count. If the decimal point is not there, you do not count. Okay? And it'll just take some practice. Any other questions? This is the section that never ends. So precision and accuracy. These are, both have this similar connotation, but they are subtly different. So accuracy says how close something is to the true value. Precision refers to how close a series of measurements are to each other, or how reproducible the measurements are. And so sometimes the analogy that they'll use is a dartboard. So I'm going to make 2 really sad-looking dartboards. And then, I don't know, we'll use green dots. So if my measurement is accurate, that means that I'm getting close to the true value. Okay? if my measurement is precise, that means that multiple measurements are close to each other. Okay, this person obviously has some sort of perception issue, right? They're very consistent, but they're consistently bad. So this is precise, but not accurate. This 1 point is accurate. You can also have accuracy without precision, because when we make a number of measurements, if we average those, the average is very close to being correct, but the precision is poor because those are scattered all over the place. Sometimes there's things we can do to control our accuracy or our precision, and sometimes there's nothing we can do about it, but we have to understand what it is. So what we're going to do is we're going to look at some data from a student, 3 students. They measured a lead block. They weighed it on a balance. They recorded the masses, and we're going to see how their results look. So here are the numbers in a table form. It's a little hard to look at this and see exactly what's going on. This is why a lot of times scientists will make graphs. So we take this data and we graph it, and we end up with this. So here's student A. Trial 1, he got this mass. Trial 2, that mass. Trial 3, and trial 4. The blue line is the true mass. It's supposed to be 10 grams. We know it's 10 grams. This student, obviously, his answers are kind of all over the place, aren't they? This is poor precision. It's imprecise. There's a lot of just randomness in here. The average of his results, 10.49, 7.97, etc., gives us this dashed line. My stylus is failing me, so nice thing. I'm supposed to be able to just tip it upside down. There we go. Get a new point. And that wasn't the problem. Oh well. There, maybe this will work. Okay, so this is the average. The average is 10.13. True value is 10. This isn't very good either. So this is not accurate, it's inaccurate, and it's imprecise. Oh, my finger works. So here's student B. So we can see by graphing it that these values are very close to each other. All those purple bars are about the same height. So that tells us that this is precise, very consistent. But the average is low. It's 9.79. The true value is 10.00. So this is not accurate. Inaccurate, but precise. And here this one, student C, has precision and accuracy. That's what we're always going for. We'd like to have both. Okay, any questions? So what causes things to be inaccurate or imprecise? There are 2 kinds of error. There's random error and there's systematic error. Random error has an equal probability of being too high or too low. There's not a lot you can do about random error in many situations. It's just there. The way you can get around random error is you can take lots of measurements. If you measure it once, you don't know. But if you measure it 10 times, the error has an equal probability of making your value too high or too low, and so when you average the results, the errors average out and you can get rid of it that way. Accuracy is often affected by systematic error, and that's an error that tends to make the result too high or too low and is consistent in that. And so that's why student B, very consistent here, but consistently too low. He has some systematic error. So what can cause systematic error? Misunderstanding what you're doing or how to use an instrument. If you're using a ruler to measure a length and you're measuring from the end of the ruler instead of from the line marked 0, That's going to give you a systematic error. All of your lengths are going to be too short. If you're using an instrument that is not properly calibrated, if the balance is unbalanced, that can give you systematic error. And so we look at our answers, and one of the reasons we look at precision is that can help us to see, okay, do we have some random errors going on here? And we look at our accuracy, and do we have some systematic errors? And the goal is to be precise and accurate. Any questions?